Hi everyone, today I want to show you how to calculate double integrals. So if you already know how to do one integral, I want to show you that the skills you have are basically everything that you need to find double integrals, okay? So let me give you this example. Let's say you have an xy plane and you have some sort of region in the xy plane, so let me do a plane. And let's say we have a rectangle. I'm going to say it has a height of 2 and a width of what? 4, okay? So our rectangle would be this, okay? And I'm going to call this rectangle R, okay? And our goal is to find the area of R. Now, this is a very trivial problem. I believe you know that you can do 4 times 2, and that's going to give you 8. And 8 units squared is the area of R. I want to show you how you can do this problem using double integrals. And I'm going to show you that you can find these double integrals in basically the same way you would calculate a single integral. So when you're doing double integrals, you're always going to have two things, basically. You're going to have, obviously, two integral signs, and you're going to have two differentials, okay? Each differential will correspond to one integral. So let's say we have a function f of xy, and here, well, now we're dealing with multiple dimensions, so the integrand is going to be typically, in most cases, a function, an expression that contains x and y, okay? And in this case, depending on the problem you're solving, y may not necessarily be you could say the output of a function. In this case, y doesn't have to be a dependent function of x, so you don't have to call y the dependent variable and x the independent variable. This depends on the problem you're solving, of course, but generally you could think of x and y as just some quantities, and we can integrate with respect to these quantities, okay? And we're gonna have, so as I said, for each integral, we're gonna have a differential. So something you're gonna have is dx dy, okay? So if you're doing double integrals, this is something you will see in most cases. Now, how can we use a double integral to solve this? Well, I want to show you that you could find the area of this region by taking little chunks of dy. And a chunk of dy, well, we know a chunk of dy would be, I'm going to do that in blue so we can see it better. A chunk of dy would be an infinitesimally, so a chunk of dy would be a very small, an infinitely thin strip or an infinitely thin region that is parallel to the y-axis, okay? So it would be this. That's good, yep. So a really small rectangle, a super thin rectangle is what we call dy, okay? Well, that would be the height of the rectangle, of course. And something you can do is, well, you can add up all the areas of these rectangles, and then you can, if you add them up, well, that's gonna be the area of the entire rectangle, okay? I think this is an idea that you've probably done before. If you've done solids of revolution in your single variable calculus class, you know that you can split an object into smaller parts and then add everything up with an integral, and that's gonna give you the total number that you're looking for. Now, dy is gonna be an infinitely thin rectangle like this, and dx, well, I'm sure you can imagine, is gonna be very similar, but now it's gonna be something like this, okay? I don't have a very good pulse, but that's supposed to be a rectangle, okay? And the idea is that this differential dx dy, notice, is going to be a square, okay? Do you see this really small square here? It has dimensions dx dy, okay? And if you multiply dx dy, well, you're gonna have the area of that tiny rectangle, of that tiny square, I guess we could call it. And if you add up all the areas of these small squares, well, you're going to get the total area, okay? And that is the meaning, that is the geometric intuition of this double integral here, okay? Now, let me show you how you would compute this. So, something we can do is, we know this region R can be split into small areas, dAs, okay? Let's call A our area, and then dA is going to be a really small chunk of area. We can do the following. We can say dA is going to be equal to dx dy, okay? And then we can say, well, you could say, you could definitely do this. You could say the total area is going to be the sum of all the dAs. And the sum of all the dAs, well, is going to be the sum of all the dx's and the dy's, okay? The problem with this is that now you have two differentials and you only have one integral. you could argue that the reason we have two integrals is to account for the fact that we have two differentials, okay? So then if we want to find the total area, we want to integrate this quantity here. And you can do this in a very simple way. You can have an outer integral, and then you're gonna find whatever is inside the inner integral, okay? So here, I'm using this parenthesis like this. So we're gonna have everything inside the square bracket is going to be one integral, okay? This is something you can do. What is the antiderivative of one? That's just x. And in this case, x will have a range, okay? What is the initial value of x of r? Well, we know r is gonna begin, the x component, you could say, of r is gonna begin at x equals 0. So our lower bound is gonna be 0, and our upper bound is gonna be 4, okay? Because that is the maximum, that is the width of our rectangle, okay? Now, this is an integral that you can find very easily, okay? So what is this? Well, this will be the antiderivative of 1, that's x, and then 4 minus 0, that's 4, okay? So then this square bracket becomes, I'm going to continue down here, this square bracket will become the integral of 4 dy, okay? Because this square bracket is equal to 4, okay? And now notice you have one integral with respect to the variable y, okay? And you can integrate this as you would integrate any other function. What is the integral? What is the antiderivative? Well, in this case, we don't really want the antiderivative. Again, we do something similar as what we did here with the lower and upper bounds. Y ranges from y equals 0 to y equals 2, okay? So we say 0 is our lower bound and 2 is our upper bound, okay? And then we integrate this. So we know that integral is going to be 4y from 0 to 2, okay? And we know, obviously, this is 8, okay? 8 units squared. And this is the exact answer we would have gotten if we had done this 4 times 2, okay? And you can see the only thing we did that involved any calculus was finding these individual integrals. Even though we had two integrals, even though we had a double integral, you can solve a double integral by doing single integrals and beginning from the innermost integral, okay? So the way in which you compute this integral, or even if you have 3 integrals, you do the same thing. You begin from the innermost integral, you solve that, and then you do the next integral in the outermost scope of your integral, okay? So then in this case, if you had 3 integrals, after we had done this integral with respect to y, we would integrate again the expression that we got from the previous integral, we would integrate that with respect to the other third variable that we have, okay? Now, these integrals are very easy, okay? And this is just meant to be an introduction to multiple integrals, and I'm gonna show you more examples of double integrals in the future, okay? But for now, this is what we have, and I hope this has been useful if this is the first time you learn about double integrals, okay? So I hope your biggest takeaway from this video should be, if you can do single integrals, you can do double integrals, okay? Just integrate the innermost, so just do a square bracket, integrate whatever you have inside, and then integrate again the outermost differential that you have with respect to the outermost differential that you have, okay? You're going from the innermost stuff that you have, and then you're going all the way outside, okay? So I think that's been the entire video. I hope you enjoyed it, and I hope you learned something, okay? I'll see you in the following one.